let me now introduce our speaker. So I'm very excited that we have Dave Schuster here to talk to us. So he did his PhD at Yale and then postdocs at Yale and MIT. And Dave is, I think, maybe without doubt, one of the most creative thinkers in superconducting qubits, new areas. He's always at the forefront. He does everything from quantum computing to more quantum simulation jobs and also projects and also things sort of at the interface of cold atoms and superconducting circuits. And so he does lots of amazing things. And he's only going to have time to tell us about one of them, but it's going to be good. So with that, Dave.
All right, is that working? Okay, great. Okay, so thank you for the lovely introduction and for having me here. It's good to see a lot of familiar faces, and as well as hopefully I get to meet some new people as well. Today I'm going to tell you about some of our so these are some qubits that we've got, but we're today, instead of thinking of them as things that we're going to make a quantum computer about, we're going to sort of think of it as a kind of an interesting physics system and just study it in that way. This kind of idea of taking things you might build for qubits and then and studying many-body physics is also often called quantum simulation, and there's many different ways of doing it. You can use cold atoms, you can use trapped ions, microwave circuits, semiconductor spins, all kinds of things, and so you might say, well, when should you use one versus the other? And I won't presume to talk about these other ones, but I'll tell you a little bit about why microwave circuits are nice. So first, as with anything, is you'd like the kind of the fun quantum interaction stuff to be kind of large compared to the time in which it becomes classical, the decoherence rate. So, and that's pretty good for us. We can get about 10,000 interactions. And I think with our qubits and microwave photons, we have really nice single photon control. So we have a lot of we can really manipulate the environment. We can control the properties of our kind of atoms, or if you will, in AutoCAD, and we can control our environment pretty dramatically as well. So. And this is something really Alicia kind of pioneered, is that you can we're not sort of limited to what lattices come from just putting a bunch of atoms together and annealing them and seeing what you get. You can do both things that would be hard to do, but even things that would be impossible to do. So and then lastly, we can because of all this sort of qubit technology, we really have very good control over each individual one. And so you can do different types of simulation. So you can as we start to get into the era of fault tolerance and whatnot, we can start to think about doing some of these things in a digital way, and I think that's going to be really exciting. But you can think of that as like quantum mathematica or HFSS or something like that. But you can also just directly treat these things as a physics system. And I have to say, I mean, again, I've adopted this sort of quantum simulation and analog simulation terminology, but actually, I don't love it, to be honest. I really just because to me that's just like what physics is, right? Like it's not necessarily a more artificial system than gallium arsenide heterostructure that we've engineered. That nature didn't just give it to us. We made it, and it's a very interesting system that has just different properties. So I think these artificial many body systems are actually just as physical and just as interesting. But we don't even know the rules yet of how to do it, and so that's kind of what we'll talk about a little bit throughout the talk. So we're going to look at you can do a lot of different things with circuits, and so you can do you can make lattices of things, and again, Alicia really pioneered this, and there's all kinds of interesting things there. We're gonna, in this talk, we're just gonna do the most trivial one you can think of, which is just like a linear chain. But we're gonna really think about interactions. We're gonna think about kind of engineering the reservoirs. We had a separate project on doing artificial magnetic fields, and that's also interesting, but not in this talk. And again, we're not the only people doing this. There's been a lot of really lovely results out of the Google quantum computer and in China at MIT and Caltech, and actually I listed Hauker, but really again this was actually all Alicia. That's her sample. So. Yeah. So. Anyway, yeah. So it's so okay. So what we're going to do so that's kind of hopefully some good motivation. But now, first we'll take you through like how do we, this doesn't look like what you might think of as a Bose-Hubbard model, but it is, and I'll show you kind of how we think about it, and how both the physics of kind of these constituents, and then how we put it together. Then what we're going to do is kind of think about how we can make and probe these sort of photon fluids. So I think the tools for studying electrons in solid state are well established. That's condensed matter experiment for a long time now. I think even in atoms and in lattices and things like that, the people have been doing that for a while. I think one of the things that I think John Simon and I, who we worked together on all of this, have been asking ourselves is like, how do we take those ideas which we think we understand well in those domains and think about it in the context of photons. So for example, photons, unlike charge or mass or atoms, are not conserved, as an example, right? So that changes things. So we're going to have to kind of reinvent a lot of the things we take for granted, but because we're inventing them from scratch, we can kind of also control them and put them in different regimes. Then and then what we're going to do is actually we're going to see if we can, with just using the fact that these things are qubits and we do have this kind of, qubit-like control over them, can we make some sort of many-body probes for actually looking at the kind of collective degrees of freedom? So we can measure sort of single qubit properties, but extract out many-body information. So we have okay. So how are we going to do this? So first, let me explain what one of those little crosses is. So schematically, it's a circuit that has a capacitor and a Josephson junction, and you can think of that as basically being the Josephson junction acts almost like an inductor, but it's very nonlinear. So if you have current running through it, it actually changes its inductance, and in fact, it's so nonlinear that even if you put a single photon in it, the inductance changes noticeably. And so you get, so when you go from G to E, you have a different energy than if you go from E to F, okay? And it turns out that that's exactly what you need for the Bose-Hubbard Hamiltonian. So you basically need two things. I'll put the Hamiltonian up in a second, but so and one thing that's confusing, I think, with all quantum computing is, right, we just use the word qubits for everything. The qubits are the memory, they're the gates, they do everything. But in this case, just to confuse you more, the qubits will be the lattice sites. So you should think of them as almost like the nuclei. If you're a solid state person, and the electron-like thing, the thing that's actually going to have dynamics is the photons, okay, that are in the thing. So we think of this as just a holder, the circuit as like a box for photons, but the fact that there's when you put a second one in there, it has a different energy. That's like what an interaction means. It means that if there's one there already, then trying to put a second one costs some energy. And there's another quirk here, which is I've drawn this in the canonical way where U is positive, but actually in our, well, actually I guess here it is negative, but our U is negative, and that doesn't matter much, but a few things are going to be flipped upside down because of it. I'll try to point it out. Okay, and the last thing is that there, there's the. Well, I'll tell you that in a minute. Okay, so we need two things to have a kind of, so we have our particles, our photons. We have interactions, which is actually the hard part usually, and then we have to have them move around, right? Because otherwise, how are they going to interact? So we're gonna if we connect them with the capacitor, it turns out that if they're resonant, they can hop. So that's going to, and it turns out those are the elements you need. So this is the traditional Bose-Hubbard Hamiltonian. And so you start out with, you have some number of particles. So that's like often called your chemical potential. And then then you have hopping, right? So you can have hopping. And again, our J has a minus sign, which, it doesn't really matter much.
Adam Schuster.
And yeah, so sorry about that. So we hop between sites, and then we also have this view, which again you can write it as a if there's it's zero if there's no particles already, because that one. But then if there's one particle already, then you get a gate. So okay, so now we can actually build that. So we've got so this is what our sample actually looks like, and we have our qubits, which I've shown the pretty pictures of a couple times already, and then we have and that's our circuit diagram. Then to read it out, we have just a harmonic oscillator. So that's what these guys are, and each qubit has its own separate readout, so we can read out each one independently, and in principle simultaneously, and then. This is more of a detail, but there's a filter to kind of prevent things from leaking out. And then we also have these lines up here, and they put a magnetic flux through this loop, and that actually allows us to change the kind of, if you think of the qubit, it basically lets us change the frequency of the qubit, lets us tune it. And we're gonna take advantage of that.
So in the qubit diagram, are those two Josephson junctions in parallel?
Yes.
Two physical Josephson.
Exactly. Yep. Yeah. And so they're not actually identical. They're actually made to be asymmetric on purpose because we don't need to tune them to zero. We just sort of need to tune them in some range, and so that makes them a little less sensitive to actually have them be a bit asymmetric. But that's a technical detail. It's basically, yeah, we can adjust their energy. This is the important piece. Okay, so we have okay, and so then the next thing, in order to work well, again, you need to get sort of a hierarchy of energy scales. And this is sort of the challenge with any kind of quantum simulation platform, is to or really any or a regular one actually, is just to have kind of, for whatever physics you're trying to do, to have kind of a hierarchy. So we want to study kind of many-body physics, so we would really like to have a significant interaction. It doesn't have to actually be bigger than J. In our case, for all the stuff I'm telling you, it is. So we have very strong interactions. You can do stuff with, actually it's quite interesting actually in the more intermediate regime. That's very hard to understand, and so interesting to look at as well. And you can also be in the weak regime. We can get our tunneling rates are kinds of tens of megahertz, and whereas then the interactions are kind of hundreds of megahertz, and the photons themselves have a few gigahertz of energy, and you can see the loss is much smaller, so it's only 25 kilohertz. So there's a factor of almost 1,000 here, and we can also so we can tunnel back and forth throughout this last many times. So they're going to kind of sample the whole thing, and we can have many interactions. Yes.
So three photons on one side is assumed to be forbidden, or is it still there? That level spacing is different from the...
Yeah, so it's actually so it is an approximation, but it's a pretty good one. So this kind of Hamiltonian, it actually works. You can make it work for many photons. I think people have done it up to maybe like 10-ish or so, but it's not a totally trivial thing in the sense that what happens is if you go too high, eventually it stops. The simple model I gave you, that it's like a nonlinear oscillator, breaks down, and it becomes sensitive to gate charge and things like that. So it turns out it actually becomes much more nonlinear and charge sensitive. So it does so there's sort of if you want to have this be more stable, you have to make U smaller. So there is some trade-off there, and happy to chat about that. Yeah. What is the frequency that defines the qubit? Like, what is the qubit frequency? Yeah, so in our case, it's around 4 or 5 gigahertz, and it's basically it's the LC frequency. So if you think of this as an L, it's just, and we can make it whatever we want, and then the C. And so the trick is, basically this U is set actually entirely by the C. And so you pick the C to get whatever U you want, and then you pick the L essentially to make it whatever frequency you want. Yeah. Great. Yeah, and feel free to interrupt me at any time. I'm happy to. Yeah. So okay. So now, all right, we have our system. Let's do something with it. So I think one thing is, like I said, these photons, if you can make the most interesting Hamiltonian you want. It could be this Bose-Hubbard one with whatever parameters. It could be something even more exotic. And if you just like wait and then see what the ground state is, there's a very simple answer. It's this. It's vacuum. Right, because the photons will, if we're in a very cold fridge, and so it's just eventually they'll all be absorbed by the walls and they'll be gone. So that's not very interesting, and that's again because photons aren't conserved like particles. And so the question is, like, how can we actually get something that like kind of has a sort of a stable phase? It's going to have to be out of equilibrium in some way, but we'd like it to be stable in a certain sense. So one of the first things we did a few years back was we said, okay, well, how does that work? Like, how does like kind of a chemical potential or that type of thing work in a regular system? And so what we realized, the kind of the essence is that if we have we have to have an object that sort of can supply photons if there's enough energy, and it will supply them, and if there's too many, it can take them back, but it won't it's just always going to add these photons in. And so we said, okay, well, how can we engineer that? And so what we did is we make a site where we drive a 2-photon transition, and so it goes up to here. But then we put that on resonance with the cavity, so that photon can decay very quickly compared to this one. And so basically, as soon as it goes up, it goes to 1, and then it's going to stay there. So this is a sort of a special site that always wants to be 1. It doesn't like to be 2 because it'll decay to 1, and it doesn't like to be 0 because it'll go to 2 and then be 1. And so let's say you have that site, but now you bring it next to the rest of this lattice, and you make it resonant, then this photon can hop over to there, right? So it's just going to hop over. And that's fine, but now it's not happy again, right? Because it doesn't have it, so it will just fill back up. But again, this one can also hop over, right? So it's going to do that in general, and now this one can do it, and so on and so forth, and this goes on and on. But when you get to here, you can't. Now you would have to go up to here, but remember that this one has a different energy by U, and if that's big enough compared to this hopping rate, it can't go there anymore. So it's forbidden. There's like a blockade. And so now the thing is stable. And if, let's say, one of these were to be lost somehow, it would just fill back up again, right? So now we have sort of this notion of an actual kind of stable object. And what's fun is we can also look at the temporal dynamics, so we can actually see how it fills. And so this Q1 is this special one that we're kind of stabilizing. But then what you can see is that when we turn this thing on, there's sort of a wave of filling, and that happens sort of at kind of almost like the speed of light or some sense, the speed of propagation of this of hopping of these particles, and it kind of goes, and then it actually reflects back a little bit, and then eventually it kind of stabilizes. So and eventually they just all 1 again, except for this guy who's kind of little bit messed up because we're driving it. And so this is cool. But it's an interesting question. Like, well, what classes of things can you stabilize this way? Because it sort of relied on some special features, right? And there's sort of two features, which actually in this system are kind of almost the same effect, but which is that if we have these, once it's full, then it takes to add another particle would cost energy. It costs essentially an omega's worth of energy here, or it's off resonance by you, so you can't do it. So that's one, and so we call that like a particle addition gap. So it's sort of or it's incompressible is another way you might say that. But not only, but there's another way that this could happen, right? Because like what would happen if this guy could like hop with two particles on this site, right? Then there'd be a hole. Right, and then this could hop over, and then you could add more, and then you can fill it up that way, right? And so you need both. You actually need two types of gaps. You actually need like a compressibility gap, like and a many-body gap in order to stabilize a particular state. And there's actually a lot of states that you can prepare that are interesting way. So this one is called a mod insulator, and that's a kind of a famous interacting. You get an insulator by interactions, but also fractional quantum Hall is in that category. So there's interesting things there. But what I wanted to talk about throughout most of the talk was actually what about if we want to make like a fluid, right? Something that where things can move around, right? Because if things can move around and you can have empty spots, then this method is not going to work, right? And so we kind of spent some time actually trying to develop different techniques for that situation. Okay, and so the basic idea is we're going to take the fact that solid state qubits famously have disorder, but so we've developed the capability of kind of tuning it out. But that means that we kind of now have individual things, and we can actually use it as a way as a resource, not just as an annoying thing. And so if we disorder it, then everything is localized. And we can have individual control and do all our qubit tricks. But then if we put it back together, adiabatically, maybe we can kind of melt it into some interesting many-body state. And now, as long as we do that on a timescale which is short compared to losing the particles, we can hope that we actually, can have a kind of a fixed number of particles. Okay, so this kind of looks like something like this. So we put some particles into these sites, and then we kind of are going to tune it. And then as they come into resonance, they're going to kind of delocalize throughout the system. Okay, but they're also interacting. Okay, so that's kind of the idea. So let's kind of build it up a little at a time. So first we have let's just do it with one photon. So this isn't many bodies, just one photon. But we're going to try to see what happens when we do it. So the idea is that we're going to start in some state. Now, you could start in here. If we start in the highest state in the disordered phase, which is just just put a photon into the highest frequency qubit, then we should end up in the highest state. We could also do it with the lowest state. You might say, well, why aren't we going to the lowest state? Well, that's that upside down U. So if you want stuff that has low momentum, you actually want to be at the top. But again, a detail. So that would look something like that. So we're going to kind of detune this disorder until it's small, and then we have this band of interacting states. And if it's a single photon, we should just end up with basically like a particle in a box, right? But now, if we were to, let's say, take the second, excited state, then instead of having the first, like kind of a particle in a box with kind of the lowest energy state, we'll end up with the second lowest energy state, which should have a node, right? So the probability would look something like this. Right? And so let's see what happens. We can try that experiment. And so now we're going to do that. And here's what the data looks like as we sweep. And what you see is that it starts to spread out. And then if you look here, that we can kind of take a cross section and look at the profile, and we get a nice kind of particle in a box like state. And if we do it for the next one, we can do that, and we see you get something that looks like like that. So it works. It's kind of cool. That's great. But you know, if for the students in the audience, like it's so easy for me to do that, right? You know, but it never just like works like that right away. And you know, I kind of said, you know, I said like adiabatic, and you know, it's easy for just to say that, but you know, what does that mean here is, you know, so basically, how fast can we do this and have it kind of stay in the ground state, right? If we go too fast, you know, we could occupy any of these states effectively. And so what you know, what the students did is they vary the how fast they kind of ramp the disorder to 0 and back, and we see what happens. And so what happens if you ramp it very quickly, what you find is you end up back in the state you started. And that's for the simple reason that basically you didn't give it enough time for anything to happen. So you basically blinked in, blinked out, and almost nothing happened. If you go really slow, then you're adiabatic. You're pretty well. Actually, if you go really slow, you see I cut off the chart here, but you see this is starting to go down a bit. Like you can kind of see there's this overall down. So if I if I go slow enough, I'll get back into the ground state again, which is vacuum. I'll lose my photons. So that kind of gives you another kind of scale in there. But if you go in this middle area around J, then you see you get more complicated stuff happening. So you know, but it's kind of nice. So we can basically, if we go, you know, essentially, if we want, we can go either, you know, slow, and then we kind of preserve. We basically, you know, kind of melt or unmelt things. And if we go fast, we can kind of preserve whatever the state was, right? So we'll use both of those. Okay, so now we did it for one photon as a warm up, but now we can do it for multiple photons. So in this case, right, we can put in, you know, we can put, sorry, we can put in, oh, let's put that up. We can put in 2 photons out of the 7 sites, or 3 or 4. And what you see is what you might expect if we didn't have any interactions. Actually, it wouldn't matter. They're bosons, so they would all just go into the same state, right? They would just go into the ground state, and it would just actually, it's not entirely true. It would be, you know, it would be bunched a little bit because they like to be on the same site. But we have this contact interaction. Basically, we say like we're not allowed to essentially have 2 photons on the same site, and so actually you get you get this kind of you know, almost you know, I guess it's kind of like a charge density wave or a straight B pattern, where they kind of are avoiding each other. So you actually get this sort of structure that's being formed through the interactions. So this is kind of nice, and actually this system in general, like, is a known system, right? It's if you have hardcore bosons in 1D, that has a name. That's called a Tonks Giorgio gas. And if you want to really probe the interactions, what you'd like to do is actually measure like a correlation, right? And we're going to do this, and so. Well, okay, yeah, all right. Well, all right, yeah. So, right, we want to see that this is actually like, you know, due to correlation. So we can just measure these correlations directly. So we have and the way you would do that is just we measure basically. We're going to measure pairs of sites, and then look at the probability that if we measure on one site, then we find a qubit on another site, or a photon on another site. Okay, so you know, if we put, let's say we have 2 particles in this box, then you know, we can think about this as 2 particles in a box. But if you imagine, you know, but there's well, you can do this both formally, mathematically, or if you in our experiment, you can think of it. Imagine you measured one of those particles, right? Then you know where that particle is, and then the other particle can't be there because there's only one, and so therefore it's almost like a wall. So so the other particle is sort of in 2 boxes. So you can, and if you wanted to think about that mathematically, you could sort of rewrite it as, instead of 2 particles in a box, you could basically say there's sort of a mean and a difference coordinate, and then and you get and that's sort of the equivalent there. But anyway, so what we do is we basically just measure, and we see that, like, for example, if we measure let's say we measure a photon in the middle box, then what you see is that the second one has this distribution which looks like, kind of a particle in a box, but in the two halves, evenly split. So you end up kind of in a superposition of the other two boxes. And if you measure it, let's say not in the middle, right? If you measure it over here, then it's going to end up there's sort of a small box and a big box. So it's a little bit more likely to be in the big box than the small box, but in both cases you get something that looks, like a particle in a box. So that's a sense in which, you can, you can observe it, and also like effectively you're creating almost like a potential from the other particle. You can also if you take this idea and you can think of this measuring these correlations as like almost like a G2 function, a pair correlation function, and you can just do that over. So taking that data, but for different filling numbers, so different numbers of particles and different positions. That's kind of question.
This might be a bit of a question. In your experiment, are you probing where the photon is, or at a particular state, is there a photon or not?
Yeah. So the question was like, are we probing like the presence or absence of a photon on a site, or tracking a photon? And it's we're measuring for each site, is there a photon on it? And in this case, because we're in this limit where there's only a maximum of one particle per site, we know that there's only it's either 1 or 0 photons there. Yeah.
So when you had a single particle, you sort of showed how slow or fast you need to go.
Yeah.
If you have more particles, sort of like you have more, like you have whatever n choose n. And
that's right.
levels,
Yeah.
You have to go sort of exponentially more slow. No.
Yeah. So this is a really great question. So the question is basically as you put more particles in, there's more possible states exponentially in general, and so then therefore do you have to go slower? And the answer is it depends on what the phase is actually. And so this is right. So if you had a spin glass like phase, then it would be a dense forest of states and with very small gaps and stuff. On the other hand, like this Mott insulator gap, no matter how big I make it, it's going to be U in some sense. So that's sort of if I'm in the Mott insulator state, it'll always be U. If I'm in one of these states where it's partially filled, it might be it depends on the details. And so so and just like when we were doing the dissipative stuff and preparing that, we could prepare certain classes of states, and other states would be difficult to prepare. If we want to do it adiabatically, that's exactly kind of is that the gap has to be sufficiently large that we can prepare it. Although, often when you're trying to prepare some a phase in condensed matter, I mean, you need to be cold enough to be in the, you don't necessarily have to be exactly at the ground state, but you at least want to be, in a subset of states that show the general properties you're interested in. But yeah, that's really critical. And I think there'll be some, I think, maybe some places to see that a little bit more as we go. Yeah. So anyway, so you can measure this pair correlation function, and this is a Tonks-Geordogas, and it's kind of this is a very small system. It's only 7 sites, but actually it's okay. I'm not saying that let's not oversell it, but it really does have that character of this fermionization, even with these tiny systems, and so actually it's kind of nice that we're in this sort of relatively small system. We can leverage the individual control that we have, and we can resolve kind of the discreteness of things, but we also get the sort of kind of mean field things as well. So it's sort of surprising to me in some sense that you can already see some of the mean field physics emerge out of such tiny systems, and we'll also see that with some of the thermodynamic properties as well in a minute. This is a little bit related. So you can also measure the entanglement of such a system. So if you take essentially, let's say you have this lattice and you take a qubit and you kind of move it down slowly and then pull it away. If if the well, okay, so if you just have a qubit and it lasts for some amount of time, you'll have some amount of decoherence, or in this case mostly dephasing. It could be loss or dephasing. You see, there's some amount. It's not zero, but as you bring it in and then pull it back out, what will happen is while you bring it in, it's sort of going to delocalize through this lattice, and then when you yank it back out, it will lose its purity because essentially it's now entangled with all of these guys. And so you can actually, by just doing essentially a dephasing experiment on this qubit, you can actually measure the entanglement, and you can see that there's a loss that's associated not with just time, but actually with how close you come to this lattice. And this is kind of another thing which, I mean, I guess it is sort of obvious, but I think this kind of vividly points it out, which is that the sort of entanglement of these systems actually kind of depends a little bit on what basis. So this is if you think of them as qubits, it's a highly entangled thing. I've actually, when I put this photon in and I showed you that single particle wave function, that's 7 qubits all entangled together, because there's one photon and it's in some correlated state. It's like a W state or something like that. But if I think of it as the photon, it's a single particle. So how could it possibly be entangled, right? It's anyway, so you can measure the entanglement, and actually you can do it for more particles, and you can show that there's more entanglement until you fill it halfway, and then actually there's less entanglement because you can think of it as holes. And this is kind of this, the same kind of physics that happens when you get like a Fermi liquid. So you can measure that, but actually we want to take advantage of the fact that when we're building these things, everything I've told you, like we're sort of we've just been putting a single photon in each site and then melting it together and seeing what happens, and that's fine. You can do a lot with that. But actually, we can do more than that, because these are qubits. So when we actually build this system, we can not only put 1 photon or 0 photons, which is already like a non-classical thing, but we can actually put like half a photon, right? We can put a superposition state in there, and we can see what happens there. And so I wanted to remind you, of a kind of a canonical experiment when you're doing any kind of quantum system, which is the Ramsey experiment. So the idea is that if you put something into a superposition of 0 and 1, and then you wait some amount of time, it's going to acquire a phase that is proportional to its frequency, the frequency difference between the two states, okay? And that's true for a single particle, and it's also true for many bodies. So if I have a many-body system, I can have one many-body state and another many-body state, and if I put in a superposition between these two many-body states, and then I bring it back together, I would get a phase that's proportional to the energy difference, okay? And so, and there's a bunch of versions of this that, you can think of anyons as being a kind of a many-body version. You can think of these like out of order time correlators, and even spectroscopy in some sense can be thought of as doing this in a certain sense. And so what we wanted to do is to take this idea and again use the fact that we're assembling these things from using qubits, and that we have full control to actually make superpositions of many-body states. So I showed you how to make a many-body state. Now we're going to make a superposition. So the idea is that we're going to take the same idea as before. So right, we saw that we know if we take this state here and we melt it, right, we'll get that single particle in a box ground state, and if we take this and melt it, we would get, or if we take these two, we would get that 2/7 state or whatever. But now, imagine we put this in, we do a pi plus, we put 1 photon in here, but here we put a superposition of 0 and 1 photon, right? Then on this many-body diagram, right, we have a superposition of these two different states. And we should get a superposition of the two different, wave functions, many-body wave functions, right? So we've got the kind of 1 particle. So these are not just superpositions of configuration, but actually superpositions of number as well, right? And And so we can, and then if we were to wait some amount of time, you can see that, this state is lower than that state. And so, we should pick up some phase associated with how long we wait and here, and then we can bring it back. And if we do that all adiabatically, we'll still end up back in these same two states. But if we measure this guy, right, this one's the same, but if we measure the phase on this one, we should actually learn something about what happened during this many-body period. So we can do that. So kind of the general idea is we're going to we'll prepare most of the qubits in some state, but then we're going to put one of them in a superposition, and then we're going to adiabatically ramp into some many-body state and wait some amount of time, and then we'll kind of adiabatically ramp out, and then we'll measure that, finish the Ramsey experiment on that qubit. Okay, that's kind of the idea, and so let's just try it out. So we'll do that and versus this, and we should get come back and then we'll see what we get here, so we're going to prepare the superposition. We're going to measure it, and then we can see some oscillations. So that's good, and then we can and so this is with 2 versus 1, and of course, I mean, we can do that for 3 versus 2 or 4 versus 3, right? And we'll get different contrast and frequency of oscillations. Yeah.
Yeah, I'm trying to understand the melt analogy, and then also that picture. So you show, since that upper picture just below the melt arrow, and the one where they're all aligned just below the melt arrow.
Yeah, so the idea is so we're going to start in this configuration where all the qubits are disordered, so they don't really talk to each other, and then we're going to put some configuration of photons into this while using our individual control. Then we're going to melt it, and then we're going to adiabatically, and then we're going to I guess freeze it again.
So they're going to the same energy states when you melt.
Well, yeah. So, in this case, we put one photon over here, and right. So that would make this wave function or probability distribution. If we put a photon here and a photon here, we would get this probability distribution instead. If we were to melt it and then just measure the probability distribution, we get something that looks like this. But what we're actually going to do is we're going to actually kind of adiabatically bring it back. So we should get essentially this instead, which is, kind of a fifth, is like this particle plus half of that particle. We were just to measure the probability. But then if we actually look at the phase associated with compared with how long we waited, it actually oscillates. Yeah.
It is related to an earlier question about how many states get populated in the So I guess I would have thought that there's a significant probability of not coming back to the same.
Yeah, I'll show you. Yeah, it's a great question. Thank you. It's always nice when people ask you about your next slide. So let's do this. We did it for one photon, right? Let's do it for the many body, and I think hopefully that will give some intuition about this. So it's really, this is one of the essences of doing many body physics, is that like how when you prepare these things, like you can have a forest of states and how are they connected and whatnot. And so what we can do is we can just do the same thing. We just prepare it, but with different ramp speeds, basically. So we can do it like with a microsecond of ramp speed, and you see that we basically come back almost completely. There's almost one peak, and then but if we do it really fast, then you can see actually several peaks in there. And so this is what the data looks like. So if we go really slow, again, you mostly have that one peak. If you go faster, you can kind of see there's this next one, and then if you go more, you can sort of see some more. And in fact, you can actually see that, and you can do this again with different numbers and see kind of what gets excited. And so you do excite not every state, but you will excite some of the other nearby states. And it depends on kind of what kind of how these guys approach each other, both their both how close they get and also how coupled they are.
These are sort of histograms over how many realizations.
It's probably, we tend to do around maybe 10,000 measurements or something, and that's mostly for signal to noise, because it's when you come back, right, one of them was in superposition, so it's a 50-50 chance, and in general. So if you want, so you have a shot noise, which is like square root of n. So if you have 10,000 measurements, you could get 1%. I mean, our signal to noise, our readout fidelities are good, like maybe they're 80-90% or something like that. So it's a little bit worse than that, but you know, you can see the signal noise isn't bad. Yes.
Are there any situations where during your RAM process, there's any like degeneracy points or like avoided mode process?
Yeah, I mean, this is a relatively well-behaved thing. I mean, we have calculated. I don't know if I'm not sure if we'll see it in the next slides, but it's relatively well-behaved. But you know, it's not a particularly bad phase. But I mean, certainly it's not like uniformly spaced or anything like that either. So.
So the energy scale at the end, the 20 meters, that's just a disorder that you put in your initial state, or is that something that's in the?
No, that's really the span. So yeah, maybe one question is like, well, how wide should this be? So it's actually pretty easy to say that. So basically, the energy span here is just like 2J, right? So basically, the energy span of these states is going to be, you know, around 20 megahertz or so.
So this is spectroscopy of melted.
Yeah, well, no, well, it is, but done in a Fourier via this Ramsey technique. So, right, we're actually right. We what we're doing is we're going in, and then if we go in very fast, you can think of the thing as being wide and spectrally wide. It's not very well defined in energy, and so it will talk to all these other states, and then when it comes back, you see those frequency components. So if we were to do spectroscopy of these states directly, we would you know see, or you know we would actually see these, you know, kind of about the mean. Yeah. Okay, so now I want to go one step further and say, okay, so we can do it is kind of like spectroscopy that we were doing before, but what we can now do is we're going to use the fact that we can sort of have this superposition of occupation to measure some thermodynamic quantities, right? And so if you, for example, if you want to measure the chemical potential, right, that's like kind of like the change in energy versus the change in particle number. And so, which in our case would just be the energy difference for adding one photon, right? So, and what we can do is we can actually, we just saw that we were making a superposition of n and n minus 1, right? And so if we just measure, and we just show that we can measure the energy difference there. So we just plot that versus all the different conditions, that is the chemical potential. So what we can do is just we just measure psi of n and n plus 1, and we can do that for kind of different numbers of particles and different configurations, and we can then plot kind of all of these out, and we can get kind of the curve here. And then if we take the differences between so this is the site number of sites, and this is and the color is number of particles. So we take kind of nearest the vertical nearest neighbors and take subtractions, right? Those are the chemical potentials, and we can plot the chemical potential versus these properties. And so what we see here is that we plot the chemical potential versus the density, and you can see that we get what you would expect for a mod insulator, which is that it's basically there is some functional form to this. It's not quite linear, but like it's nice and smooth. But then if you try to add one too many particles, there's a big gap, right? So we can measure the so we can measure the chemical potential. We can also I like this one even better. We can measure like the compressibility, right? So and then the pressure, right? So pressure is like dE dV, right? Thermodynamically, and so you're like, well, how can we kind of change the volume? Well, there's a trick, which is if we have a let's say we put a particle in, then actually now if you want to basically, if let's say we detune a little bit, right, then having no particle in here, you actually can't jump, right, because there's the level's not lined up. But if we put a particle in, the next level is at a different energy. So if we make it so that like you can jump in if there is a particle there, but you can't if there isn't, you've made a superposition of volume now. So not a particle number, but a volume, which is kind of a weird thing to do. And so that gives us that gives us sort of a quantum version of our d volume, and d we showed you how to measure, so we just do that again, and now we can actually figure out what is the pressure of this thing, of this many body system as a function of the density. So that's also kind of nice, and the theory is just from a kind of a, again, we use this Tongsteer-Do kind of fermionization kind of thing. So we can do pressure, and how are you doing on time? Yeah, we're okay. So we can also use the same idea to kind of make some other interesting states. So that, okay, this is maybe a little bit more quantum computing-y, but it's, I don't know, it's still kind of neat. So I want to show you, which is that we can make what's called a noon state. So a noon would be like, which is like it's n particles here and 0 over here, or n particles over here and 0 over there, and so or you can think of it as the photons are in one of two boxes, but they're all in this box or that box, right? And so what we do is we use this fact that if there's a photon in here, we can move through, but if there is no photon, we can't. And so it's basically like having a superposition of a wall here. So the same thing what we did at the end, if you put it in the middle, you've got now a superposition of a wall between the two things. And you can, if you slide through, then there's actually a gap where basically essentially, right, when these guys are, when right now, like, right, the photons are in the highest state, but if I sweep them through, those guys will be the highest state. So at least if we go slowly enough, it should move over. Okay, so we can do that, whereas here nothing happens. Okay, so that's kind of the idea. And what you can see is that actually works. You can adiabatically kind of transfer in this case and not in that case. But now if I make a superposition of these two, I should get a superposition of these two. And so we can do that. And we do this. And again, now we're going to use our same many-body Ramsey interferometry trick to measure it by just measuring it. If we do Ramsey on this middle qubit here, we should be able to measure the energy difference between those two states. And what you get here is that you get some fringes. But what's cool is that actually the slope is faster, right? Because if you have one particle, you would have you'd see the energy there. But if I have two particles, it's going to be twice as much energy. So you can actually see, and in the slope, you can actually see that it's higher for when you have a pair versus just a single particle. And you can do it for more too. You can do it with 3. That's all we can do in this system because we only have 7 sites. But in principle, you could do it with more. So the problem is that, like, you can kind of see that, like, okay, by the time we're doing these, you can start to see that when we were doing simple things like these, the contrast was pretty good. Now it's getting a little gnarly. So we have our postdoc, Andre, who's just started a faculty position at NYU, had a very clever trick, which is that, it turns out this is limited by our dephasing, not by our lifetime. So like our T1 is longer. And so when your dephasing is shorter than your lifetime, you think about a spin echo. But this is sort of a many-body state, and so how can you do it? And it turns out if you look at our sequence, right, most of our time is actually spent like kind of, so we prepare our state, we make our superposition, then we adiabatically ramp, then this is the phase we're actually measuring, then we have to ramp back up, and then we do our thing. But if you look at the actual kind of time spent, most of it's in the blue there. It's in these ramps because we have to go slow. So if we could echo that out, we could do it. So we're going to do a weird thing, which is we're going to go slower. So we're actually going to make 2 copies of this. So we're going to go in and out. And then we'll go in and out again with the actual, but with a weight. But we're going to put a pi pulse. So we're going to reverse the sign essentially of the precession of the qubit in between. And so even though we're taking longer, but we have enough time with our T1, and we're not perfectly balancing it, but we're sort of balancing this part, and we're just not balancing out that part, which is the part we care about. So now we can look at the thing, and so you can see with without the echo, I mean, you still see it, but and you can still get it, but it's kind of gnarly. And with the echo, it's significantly better. And so we can do that. Okay, so that was I think we're just on time, so we'll end there. But so we kind of saw how we can assemble fluids of light, both dissipatively and with these adiabatic ramps. And then we saw how we could sort of assemble superpositions of these many-body states and then do single qubit measurements to actually explore kind of their spectrum and how they depend on things like even thermodynamic quantities. And then, I think there's a lot of fun things, right? We can you could imagine doing more complex lattice topologies. You could do, there's maybe something in between the kind of particle dissipation and the purely adiabatic, where maybe we could have relaxation within there and photon cooling, that kind of thing. So these are all kind of directions we're interested in. I want to, of course, most importantly, I didn't do any of this. It was, of course, it was a group, and in particular, it was Andre, Gabrielle, and Brendan who actually did the work. Yes, so Andre is now a faculty at NYU. Gabrielle was doing that most recent error correction paper at Google. Brendan is at IBM, and all of this work is actually a collaboration with John Simon's group, and it's kind of a nice thing. And I think that's why especially here at JQI, that probably resonates because sort of we think we both think about cavity QED, but from circuit perspectives and from atom perspectives, and you can see sort of I think some of the inspirations from both sides in that. And so thank you for listening, and I'll just leave that up there, which is other things that my group does. Yes.
Thank you for the stuff. So I was wondering if, because of the ramp being the limitation to your increasing time, we consider using counter-diabatic drives to make it go faster without compromising on the adiabaticity. Yeah,
so I mean, I guess the question is always like, for these many body states, like, sort of like what is the other term you have to drive in order to do it? But yeah, I think, I mean, in some sense, figuring out how to prepare, start in some known state and then prepare like an arbitrary many-body state that is actually, like in some sense like an NP complete problem. So it's in general, it's not possible, but for any given class, there can be tricks to do it. And I think, trying to understand that which states can be done and which states can't is interesting from a complexity sense. And specifically for different classes of interesting states, how to do it. I think it's quite an interesting question.
Last experiment, it seemed like you had a revitalization for the high fall setting. Is that from leading, or are you seeing the fade? I guess
Yeah, no, yeah. So you're very observant. Yeah. So if we look here, so Ben's question is like, why? There looks like there's some structure in here. It doesn't look just like random noise or like it's just small, and that's right. And the reason is because when it's basically there's the nearby states are more likely to kind of pick up some weight than others essentially, and there's a sort of a balance between how fast you're going, like right, you're sort of balancing like if I go faster, I'm going to have less dephasing from the qubit, but I'm going to populate these other states more, versus if I go slower, then I'm just gonna lose my contrast, but I'll kind of not end up in other states. So I think I mean, it could be other things, but like it could be a TLS or something also. But I think it's actually the fact that there are some frequencies coming from the many-body, and we just don't have enough contrast to like observe it in the spectrum, even though they're there.
So what's the next device in the project?
Oh yeah, so I mean, I would say we're actually thinking about a number of different things, but one device we actually have out for fabrication is actually, we said, okay, well, what if one nice thing about quantum simulation compared with quantum computing, for those who do both, is that like in quantum computing, you really need like, ideally you want your first qubit, you want your qubit to be perfect as much as you can. Then you add a second qubit, you want that one and the 2 qubit gates to be good, and then you grow, and you have to keep really full control over everything, and that's hard because there's it's hard to improve one thing while keeping everything else excellent. In this kind of more physics based stuff, right? We really want like the essence of a property. We want to learn something from it, and that allows us to pick one thing that we want to do special, but potentially at the cost of like giving up some other things, right? So and so we decided one thing that'd be interesting would just be to go to a much bigger system, and but not necessarily having to control it fully. So one thing we're trying is to say, okay, well, we saw that we can actually learn almost everything we wanted to learn about it from from just a few qubits that we could control really well. And so if we can, so what we're doing is we said, let's have a static non-controlled set. So we're going to just put a whole bunch of qubits that are coupled together, and we're going to put them in this more intermediate regime where J and U are kind of more similar, so it's even harder to understand. So it's going to be a big mess. And what can we learn about that system just having a few kind of probes? So we have qubits or entangled pairs of qubits that we can put in there, and can we actually learn what that Hamiltonian is and what the interactions are, and understand it from that? So that's one direction. We also we're having, and I think actually as just like a philosophical point, actually that's one reason I really like doing these experiments, is because of course we can take the technology we're developing for quantum computing and use it for understanding basic physics, but also it kind of it gives us a little bit more freedom to try something that like we know we wouldn't be able to get right on the first try in a compute at the level we would need it for computing, but it pushes us to think about it, and then once we understand it a little better in this context, then often we can bring it back, and that's definitely happened in a number of cases. We also are thinking about some other types of dissipation engineering with mixtures of oscillators and qubits and things like that. So I think there are at least some directions. But
one last one, and then.
So this is kind of related to your comment just asked. So how does T2 variation across your 7 qubits affect these experiments? Because I'm assuming they're not all having the same T2.
Yeah, so I mean, the nice thing is it's not as terrible as you might think. Like it's not so, again, because we really are. Right, like a lot of what so for obviously for these measurements that matters, but it's largely kind of the contrast. So if we're willing to average more, we can still do it. But as long as it's not too bad, like we will tend to stay in the same state. So all the kind of stuff, the story I told you will hold. But that being said, like that's what made the I show you the pretty pictures. The students have to fight with the sample. So like one big thing was like there's a lot of that kind of stuff that they had to deal with. Which so there's for example there's these TLS things that are basically there's kind of these points in frequency space where there's another like microscopic resonant system inside the qubit, and when you sweep through it, you can that qubit can actually die basically, and so we had to do very careful spectroscopy of this whole system, find it, and try to figure out places where we could in paths which we could do that. There's all kinds of like crosstalk mechanisms that can happen even in this disordered state that they had to deal with. So there's a lot of technical things, and I think and it is a fundamental issue with this approach in some sense, which is like as you try to make it bigger, there's like many body kind of things, like the density of the energy levels, right? That's like a fundamental physics thing, and even complexity theory kind of question. But there's also like these sort of technical issues about what you can and can't control, and I think we can we can understand the physics better, of course, we hope, and I think the technical things that we can, I think there's also interesting technical solutions there, and I think some of which we'll get for free just as the quantum computing gets better, and some of which when we fix there may help the quantum computing.
Why don't we thank Dave for the